Thanks very much for Olivia's invitation. It's my great honor to present, I think, my second talk in GERAD. This is quite hardcore and technical work about the price of fairness. And this is joint work with my PhD student, Yichuan and Professor Daniel Granite, both from UBC Southern School of Business. And I would have to say that my PhD student, Yichuan actually took most credit for this work. So let's see what we are doing. Okay, so we're talking about fairness, right? There are many applications with fairness issue. I could easily nominate some. For example, kidney allocation, right? Have limited number of kidneys you want to give to different patients. Air traffic scheduling. Air traffic scheduling, mainly, I think there are several things which are scarce resource. One is the runway, right? The runway, you need to assign the runway to different airlines. And also the airspace, you need to allocate the airspace to different airlines. And there is a fairness issue here because I think that their paper consider that if you don't align fairly, some airline will face like a big delay. Right? No airline wants to have a delay. So there's a fairness issue here. And the water allocation problem, that is quite, I think this is also like quite straightforward, right? Like resource allocation, medical resource allocation, carbon allocation, this is in the production system. So all those are about the scarce resource allocation, then there's a fairness issue. And actually, this year's informed case competition finalists, actually two of those cases are about the fairness issue. So which just indicate that the fairness has been more and more studied in the literature, particularly by the growing concern with the EDI, right? So that's why fairness now plays a real role. And one big motivation example I want to use is the kidney allocation by Stefanos Zinius. He is talking about how to distribute a limited number of kidneys to a long wait list. So only some patients from the long wait list can get the kidney. So that is a really question of who dies and who lives. So this is a very important question here. And there's the efficiency side, right? If there's only fairness, it's easy. You have to do first come first serve. That's like the golden rule for fairness. However, there's the efficiency. Efficiency means different kidney and different patients, the match will generate different utility. This utility can be scientifically measured by the quality adjusted life years, by the expected quality adjusted life years, because there's a mature way to predict which type of kidney, if by being allocated to which patient can generate how many life years, right? So that there is the efficiency measure. So there are two objectives. One is the efficiency, one is the fairness. Right, so this objective, however, sometimes is conflicting with each other, right? If you want to be fair, if you want to be efficient, then basically you should give the kidney to those younger people. But then that will create huge waiting time disparity between the young people and the older people, right? So that's I think a conflicting. So this objective is conflicting. So what we should do here, what we can do here is the decision maker had to know, right? Usually the fairness is in a certain way of constraint, right? We want to subject to those fairness constraints, then you maximize the efficiency. So we want to know that quantify the efficiency loss due to the constraint of the fairness constraint. So if you add the fairness constraint, then the efficiency will go down. But without those constraints, of course, then your optimization has less constraint and you could achieve a higher efficiency. So we try to quantify how much loss it will incur by adding those, imposing a certain fairness ratio criterion. And we try to derive tight bounds, right, for those fairness loss. Because this fairness loss has been actually proposed in the literature, right? It's called the price of fairness, the price of fairness. Okay, so mathematically, that is the formulation. Maybe I could have. So a central decision maker needs to allocate a scarce resource among finitely many players. And there is a set utility set, right, which could comprising all the achievable utility allocated for the players, which means achievable. So if there is a certain allocation among the users, so different users have maybe U1, U2, U3, if there are 3 users, right? So a set, if U1 equals 1, U2 equals 2, U3 equals 0, if that can be achieved by a certain allocation, then we say, okay, that is a feasible allocation. And this point will be comprised in this set U, right? So we assume those U, this U, right, have certain property, right? So this is a achievable utility set for all the allocations, that we define that's a capital U as all the achievable utility set. Okay, and under the this is called the utilitarian principle. Which means CDM just to try to maximize the summation of the utilities of all the players. So that's a one solution. Whether it's fair or not, that's a different question. But this is called a utilitarian solution or utilitarian principle. So I just try to maximize the lump sum of all the people's utility. And in many applications, however, you cannot just use the utilitarian solution because you need to consider fairness constraints. And we consider in this paper two fairness criteria. One is called proportional fairness, right? The other is called max-min fairness. So we will provide the detailed definition in later slides. And quantifying the relative system efficiency loss, basically you quantify if you want to implement this proportional fairness solution versus this utilitarian solution, what's the relative efficiency loss, right? Of course, the utilitarian solution will be better because we measure the efficiency by the lump sum of the utility. So if you are just maximizing towards the lump sum, of course, that's always gives the best efficiency. But if you consider fairness solution, right, then there will be a fairness efficiency loss. So that efficiency loss is defined as the price of correlation. Okay. So what our contribution is, so by given both for both the proportional fairness and the maximum fairness, right? And there are two different conditions for the sets. One is we assume every person have an equal maximal achievable utility. Another assumption is every person may have a different maximal achievable utility. So in the previous paper, so this paper we will mention it many times in our paper because that's the seminal paper by Nicholas Trikakis, Vivek Farais, and Bertsimas, Dimitris. So in 2011, they first proposed this idea called the price of fairness. So this price of fairness idea is proposed by them, and they also prove some bounds. They prove, but their bounds is mainly tied in the equal maximal achievable utility case. Basically, they assume everyone had the same largest utility. So you basically could normalize everyone's utility by 1. Which 1 means if you give all the resources to that person, he can get the maximal utility 1. Right? So this means that every person's maximal achievable utility is the same. So that's under this assumption, their bounds are almost tight. It's not really tight in this case. We'll talk later, but they're almost tight. But their bounds are not tight when different players have different maximal utility, achievable utility. People said, so that's a question, is that meaningful? The first question, right? If this is already good enough for modeling purpose, then why we bother to consider that case? Because in that case, their bound is already almost tight. But the question is, is that always fine to assume every player, their maximal achievable utility is 1, let's say. Right? Can you
define a little bit more what you mean by this maximum achievable utility?
Oh, sorry. Yeah, maximal achievable utility means if I give all the resources like to this person, so I try my best to maximize this person's utility, then what's his achievable utility?
I understand this, but how does it work to have indivisible product?
That's a very good question. If it's indivisible goods, actually your utility set maybe even not continuous, right? Actually, that we don't consider. We assume the utility set have to be convex. So I think that already rule out the indivisible.
We started by talking about this kidney problem. So here, I have it or not.
That's a very good question, but there is a randomized policy. So even you said it's indivisible, but if my policy is a randomized policy, actually I still can model it. Right? I could have a probability give you with a 0.6 something like that. Then that even indivisible, it still can model that.
So you can convexify the set.
Yeah, convexify the randomize.
How do you implement after that?
So I said, you give me a score, maybe he give me a score, right? I said I allocated the kidney in probability, maybe 60% to you, 40% to him. Whether this 60% is decided, calculated based on the score, based on your score. And people said, oh, how can you do lottery, right? How you do lottery? In kidney allocation, actually, in kidney allocation, you cannot do lottery. But actually, kidney allocation, you could do randomized by waiting time, right? Because the waiting time, actually, you could consider who comes first. That's more like a random stuff. Yes.
Thank you.
Yeah, thank you. But so here, I think do you want to explain the maximum achievable utility? Why considering that case is important? Can you just normalize everyone's utility is one? Right. So if you are just using, if this utility doesn't have a practical interpretation, it's just to measure everyone's happiness or satisfaction, then actually you could just use it's called a cardinal utility. You could just normalize to one because this utility function is only used to measure your own preference, right? So your magnitude doesn't matter, or it can be up to any positive scaling, affine scaling, right? So that in that case, actually you don't have to consider that case. Right, because everyone you just normalize it to be one. However, in cases like kidney allocation, in cases like the air traffic scheduling, every person's utility actually have an objective unified metric. Like in kidney allocation, the utility is the quality of adjusted life years. So basically, everyone's maximal achievable utility is different. A young person's maximal achievable utility is different than the older person's maximal achievable utility, right? So in that case, you could see it's not unreasonable. You assume everyone's utility you could equalize, normalize. So that I think in those cases when there is a unified metric for everyone's utility, then you should consider this. Also in the economics, like Euro-Danborough exchange markets, right? Everyone's had the initial endowment. WI, right? Initial, so that's his initial asset, how much money he has. So basically, different person has a different amount of money, initial endowment. So in that case, also unequal maximum makes sense, and you cannot model in this way. And so all those cases point that there's a significant actually to consider the unequal maximum achievable utilities. And in that case, the Bertsimas, the famous papers, the Bertsimas, their bounds is not tight. And we could improve it, and we also prove our bound is tight. Okay. So that's our main contribution. So I said actually this paper, the main content is just can be just summarized by one slide. So all the rest we're trying to basically maybe to show the technical detail and the proof. But the main message is that we tighten the bounds. Actually, this talk is just one sentence. We tighten the bounds. Okay, so then let's go to more details. So let N denote the number of players. Let U denote the set of all achievable utility allocations to the players, which has to be convex and compact. And we leave it for future research question. If not convex and compact, we are not sure how to deal with that. So we do need to use the convexity. So this utility set is convex and compact, right? And the justification is what I said. You could use randomized policy always to convexify, right, the possible allocations. And the utilitarian allocation is an allocation that maximizes the sum of all players' utility. But as we said, this U star denotes the utilitarian solution, which maximizes the lump sum of everyone's utility. And the proportional fairness allocation that is defined as this one, as this mathematical formula. So this allocation maximizes the sum of the logarithmic of the allocated utilities. So basically, it's not argmax, the sum, but the sum of the log, right? And why this is that this is not the original definition. Original definition is that this function has to so you cannot decrease one person's utility by 10% in exchange with other person's utility increase more than 10%. This is more like the original definition for proportional fairness. Right, so if you decrease anyone, if you want to increase any person's utility by 10% more, you have to decrease another person's utility by at least 10%. So that is the proportional fairness definition, right? So, but it can be equivalent to this condition, not just maximize the logarithm. And the max mean fairness is like it's lexicographically maximize and order the vector of the ratios of the players allocated utility to their respective maximal achievable utility. So what does that mean? So we can, for everyone, he had a maximal achievable utility, and he has a utility corresponding to the current allocation. So like if according to the current allocation, right, someone had a maximal achievable utility 2, but he only got 1, so his ratio is 50%. And someone had achievable utility, highest achievable utility like 10, and he get his current utility also 1, then just 10%. So you have some people get 10% of his maximal achievable utility, and some people get 50%, and some get 30%. So if you take the mean, so that's the max mean. You first take the mean. So then, like if it's 10%, 20%, 50%, then that's 10%. You try to maximize the 10%, right? So that's a max mean fairness. So you try to maximize the minimal ratio among all the players. But the thing is, sometimes there is a tie, right? If both people get a 10%, then we should also look at the 20%. Right, so this basically is we said it's a lexicographically maximize and order the vector of the fairness of the players. So that's a max mean fairness. Okay, so this n equals 2, this UPF coincides with the classical Nash 2-person bargaining solution. And this max mean fairness solution is just a KS allocation. So there are some literature talking about that. I just try to link to the classical concepts in the literature. So this is our definition of a utilitarian solution, a PF solution, and an MMF solution. So max mean fairness, PF means stand for proportional fairness. Okay, sorry, then that's the price of fairness is defined as that. So you have a utility set U. This fair depends on what fairness criteria you're using. It's a PF or MMF in our paper, right? So it's the sum. So this basically this is the efficiency measure. That's a lump sum of the utility minus. Under the fairness solution, what's the total utility? So that's your efficiency loss, right? But we are where this price of fairness is defined as relatively to the utilitarian solution, right? So if without the fairness solution, you could get achievable you could make an allocation that the total utility is 100. Let's say after you did the after you impose this fairness solution, the fairness solution either PF or MMF. Then it only get like 60. So then your price of fairness is 40%. It's 0.4 because original 100, and now you only get 60. So you lose 40. So therefore the 40 is your price of fairness. 40% is your price of fairness. Okay. So we try to get we try to upper bound, derive an upper bound for this. Okay. So we consider the cases that where fair is either PF or MMF. Okay. So this is what we try to do. We try to derive an upper bound for the price of fairness. Okay. I think why we don't do the lower bound? The lower bound is usually trivial, right? The lower bound is usually 0 because you could always construct something make it equal, right? So the lower bound can be trivial, but we are considering the upper bound. Okay, so BFT provide an upper bound of the price of fairness on the proportional fairness with equal maximal achievable utility as follows. Right, so basically that's their bound. That's not our contribution. That's in 2011. So they show that for proportional fairness, as long as the utility is convex, right? Actually, your price of fairness is at most that much. At most that much. So this is the result, and this bound is quite close to 1. You will see when n go to infinity, this bound is quite close to 1. But this is basically all the POF actually we saw. Indeed, the worst case you could consider any utility set, right? You could always find some utility set that makes the price of fairness very, very large, close to 1. Right? And I said the lower bound is usually trivial, because you could always construct a utility set to make the price of fairness to be 0. Basically, the utilitarian solution and the logarithmic solution, they are coincides, right? Then the price of fairness is 0. But those are not interesting cases; those are special cases, right? We are considering the worst case, basically. So that is this is in the literature, and this bound is tight. They also show if n is a square root n is an integer. So n is like 4, 9, 25, right? 100, like that, right? So if the number of players is tight, is an integer, then this bound is tight. Tight means you are able to construct a utility set. For this utility set, the price of fairness is exactly that much. Exactly that much. So this is our result. So our results improve that. So in n equals 2, that n equals 2 is not that interesting, but in general n, we give this bound. It's a bit complicated, right? But so for if epsilon is smaller or larger than that, so we define epsilon as so it's n like this way, right? So because for n, if it's not an integer, square root n is not an integer, like n, if for example is 8, right? If n is 8, then k is 2, right? Epsilon is less than 1, right? If it's 1, it's 9 because, right? So if it's 8, then it's between 4 and 9, between 2 like squares, 4 and 9. So k is 2, then you plus some number, right? Plus some number. So depending on this epsilon is less than this number or larger than this number. So epsilon must be between 0 and 1, right? But if it's larger than this number, then the bound looks like that. Otherwise, the bound looks like that. But in either way, that's an explicit bound, right? Those are explicit bounds. So we derive a closed form bounds when the players have equal maximal achievable utility. Because in the equal maximal achievable case, the Bertsimas bound is not tight only because they are tight only when n is the square root of the integers. Okay, so when n is not a square root of the integer, then we could improve their bound. We could improve their bound. Okay. So maybe we could very briefly talk about the proof idea, right? So for any convex compact, that's why we need to use convex compact. So you have original utility set U, okay? Because if consider the PF solution try to maximize the sum of logarithmic functions. So the sum of logarithmic function, that's a concave function. That's a concave function. So you are maximize the concave function over convex set. So what you know, if you are maximize the concave function over a convex set, then you know the maximal is always achieved at the boundary, right? So it's at the boundary. So you could use like a basic separation theorem. So then what you know that you could augment this U to U prime. So U prime is like a polygon. So original U doesn't have to be polygon. It's a convex set, it can have strange boundary, nonlinear boundary. But those nonlinear things are ugly. We don't want to deal with that. We could augment this U to U prime, make sure U prime and U have the same maximal with respect to the logarithmic function. So if you try to maximize this function, you maximize over U prime and maximize over U, they have the same solution. They have the same solution. So that can be done because this is a strictly concave function, right? And U is a convex set. So you could use the hyperplane lemma to get a polygon U prime. Okay, the nice thing about U prime is that U prime will have the same proportional fairness solution as U. But of course, it's an upper bound. But why? Because the utilitarian solution may change, right? If you maximize utilitarian solution, then maximize over U prime and maximize over U, they are different. They are different. And that's why we said this U prime, if you analyze U prime, it gives the upper bound for the price of fairness. Right? It gives the upper bound for because you increase the utilitarian solution. You increase this objective function, but keeping the fairness objective function the same. Right, but your utilitarian solution, you actually overestimated the utilitarian solution. The original set is U, actually you augmented to U prime. So that's the key idea. People said, well, you lost too much. You don't lose too much because your U, in the worst case, could be U prime. Right, because I'm considering the worst case. The worst case you could just be U prime. Then the bound is tight. Okay, so that's work on the U prime. Okay, so if you work on the U prime, the problem basically reduced to this form. Right, so this form, so you are trying to basically maximize the price of fairness equivalent to 1 minus this, right? So you are just basically equivalent to minimize this ratio. This ratio is the fairness utility, the utility at the fairness solution divided by the utility at the utilitarian solution, and this can be further expressed by this ratio. Right, this CI is basically the hyperplane for U prime, right? This is the basic hyperplane to separate the given the concave function, you could separate it, right? Those CI, so this CI you don't know, those I don't know, but you try to minimize this ratio over all the C and the L. Okay, the L has a separate constraint that the first L should less than 1, L plus 1 go to I greater than 1. Okay. So that is basically what we try to work on to upbound this the upper bound of the POF is equivalent to minimize this. This is I think a linear program. And sorry, it's a nonlinear program. It's a nonlinear program. The objective not linear. Right. And if you look at here, actually this is more like a knapsack constraint. Because you are basically trying to get L items, right? With a volume, each volume is CI, the volume total up to be less than maybe the size of the bin, which is 1, right? And you try to maximize those things. So the denominator is more like a knapsack problem, but it's different from knapsack problem because now you minimize the ratio, right? So you're not maximize the denominator, you are minimize the ratio. Okay, so let's see what we try to do here. We can try to characterize the optimal solution, right? We try to prove the optimal solution to this problem must satisfy those properties. So for all those I greater than n, CI should be 1. For all those I less than L, L is the largest number such that CI summation is less than 1. So all those before L, this CI should be between 0, 1, and it should be equal. Okay, and the CL plus 1 must be 1. And actually, later we prove actually they are equal, but they are equal to 1 over L. So we prove that the optimal solution must be that. So basically, we could write out the optimal solution then, right? So the problem then from here will be reduced to here. Will reduce to this problem. So after you then how to solve this problem? You have L as integer, right? If you solve this problem, actually it's a basic algebra, just because it's very straightforward. L is the integer here, right? And here you are using the geometric sum, average, something like that. So you could derive the final results, right? So this proof is not that involved, right? But mainly we're using the basic separation hyperplane idea. Then we prove that this result, right? So this slightly improves over Bertsimas bound. What means slightly? Because if you look at the relative, right? The relative improve. So the relative improve is in blue. So if blue is 0, basically it means no improvement. So this is the relative improvement of unbounds than the existing DFT. DFT stands for Bertsimas, Farias, and Trakakis. This is 3 MIT guys. So basically the relative improvement is like that. Most of the time 0. So there are no improvement. So and we proved that the largest improvement we could achieve, actually, the largest improvement we could achieve is when n equals k times k plus 1. Right? So it's like 2, 6, 1 times 2, 2 times 3, 3 times 4, 4 times 5. Like when at the end, like those values, we achieve the most achievable, biggest improvement. Also, the improvement also shrinks when n go to larger. Okay, so this is our result. What is the intuition?
This result that you improve on this property.
The qualitative insight is 1 is when n is larger. The price of fairness is larger, actually close to 1. Actually, not close to 1, but it's increasing. But the other is our improvement over the existing bounds is mainly achieved when n equals to like k times k plus 1. But when k equals to k squared, we already know it must be 0 because that's a tight bound. They already proved that it's tight. Okay. So we cannot improve further. Yeah, but basically their bound is already quite tight. So we can't do much, right? It's a slightly improvement. I know it's not maybe not very impressive. It's a slight improvement. So that's the first result. That's when all the players had equal maximal achievable utility. Okay. So then we also then we try to do the unequal case. So that's the more interesting part because in that place we could actually improve significantly because that's unequal, right? So this is the BFT provides an upper bound, so that's their bound. Their bound said POF of U price of under the proportional fairness it's a bit similar, but there's some other item here. So it's an explicit bound, maybe not very beautiful, but it's a bound, explicit bound. So what we can do, we can we denote the maximal utility of player I by Li, right? So different players have different Li. We assume Li are different, right? And we assume Li is decreasing order without loss of generality. Then we assume we derive the bound that looks like that, right? So if depend on the values of the maximal achievable utility, there could be two different bounds, but they are both explicit bounds. Right? They are explicit closed form bounds. And the above bounds will prove that's tight. Tight means you could always find this U, which makes it equal the price of finance. Right? Find a U such that it equalizes, the bound is tight. Okay, so this bound, how much time I have? Maybe I was 25 minutes left. Okay, so I will skip maybe the proof. The proof is the first step that I did similar. So you try to find the U, you augment the U to U prime, such that they have the same price of proportional fairness solution, but the latter had a larger utilitarian solution for the U prime. Then you that reduce the program to this form, or that's actually exactly the same as before, unless originally this LI are all ones. Now they are different LI because the maximal utility are different, right? So they are parameters. The LI is like the parameters. We assume they are monotonically decreasing, but that's it, right? So this linear program become more complicated because those are the LIs. So then we could also try to characterize optimal solution. The CI looks like that, right? CI looks like that. And then we, it's more complicated actually than before. It's much more complicated than the previous case. So it reduced to this problem. Then this problem, we need to characterize the optimal solution again. Then we find that the optimal solution satisfies these properties. And then more this, because of time, I just concluded that after you do many of those algebra, those tricks, then you could characterize the optimal solution in this way, right? In this way. Okay, so that is our bound. So now you could see the improvement is significant because this is the red one in the BFT bounds. It's upper bound, and our upper bound said it's tight. It's like that. So that's a significant improvement. Right? That's a significant improvement because you look at it here, right? Their bounds could be 0.9. Could it be 0.9? If it's the price of fairness 0.9, basically that means the price of fairness is almost 1. It's already less interesting, right? But we show actually the price of fairness is only 0.6. Right? And that's, of course, it increases with the sample variance. So that's another insight. If the maximal utility has more variance, the price of fairness tends to be larger. So the unequal case, indeed, is more difficult to derive upper bound or derive upper bound because the price of fairness tends to be larger when there's a variance in the maximal utility, right? But in this case, we improve over BFT bound significantly. And we showed our bound is tight. So you cannot do better. You can't do better. So this is the best we could do. Okay. And so this we generate the LI like randomly, right? So if you don't believe you could try to generate your other L, it's more like similar, right? So basically in that case, our improvement is significant. Okay, so this concludes the proportional fairness solution, right? And actually, in the worst case, right, we do show that the upper bound can be 1 minus 1 over n, right? So indeed, we show this even it's tight. We show actually the price of fairness is large. It's close to 1. 1 minus 1 over n, and we theoretically could show that. That's life, right? Previously, they said they had upper bound, but they don't know the upper bound is tight or not. They don't know really the order. Now we could show the order is 1 minus 1 over n, and you can't do better. Right? What can't do better means I could always find those LIs, the maximal attribute utility. If you design this LI like deliberately, then the price of fairness could be as worse as 1 minus 1 over n. And that actually also this is 1 over n, not 1 over square root of n. So that's even worse than we expected. We first thought it's 1 minus 1 over square root, and it looks like 1 over square root, but actually it's 1 minus 1 over n. As worse as 1 minus n. Okay, so this is the we close that theoretical gap between Bertsimas paper and the true, which is the price of fairness for the proportional fairness. And then we talk about max-min fairness, max-min fairness. So their paper show that the price derive bound for the max-min fairness, and thereby this bound is tight when utility when different users have an equal maximal utility, right? So if in the equal utility case, that bound is tight. It's not like the previous PF case that it's tight only at when n square root n is integer, right? This is tight for any n. Okay. So basically in that case we can't do much. It's already tight. But for the unequal maximal achievable utility, they have a bound, right? They have a bound. They have the same bound. They basically use the same bound. We said we could improve over their bound, right? In the unequal maximal achievable utility case. Okay. So this basically say, okay, it's a closed form bound still, right? The closed form bound. I know the set is a bit like ugly. But basically, that's a closed form bound because as long as you give the LIs, you could judge which set is empty or not, right? So if SY is not empty, it's this bound. If SY is empty, it's the second bound. It's a closed form bound. Okay. So the proofs, I don't think I have time to go over, but still, the first step is to use basic separation and reduce to this problem. But this problem is actually more complicated than before. And you need to do many reductions, right? The whole paper is actually working on how to do reductions and to show that the different cases. It's super difficult. I would say. I'm sorry. I want to say it's. I don't want to say it's difficult, but I want to say it's super. It's not a trivial. Right? My point. It's not a trivial. Right? So basically, you need to nail down different cases and show that basically the result. To show the bounds I just showed you earlier. And the bound is significant. The improvement is still significant. That's BFT's bound. That's our bound in the unequal maximal utility case. Although that bound is tight, if you have equal utility, that bound is tight. But the unequal utility case, the improvement is still significant. I can say improvement is still significant. And again, we can show that in the worst case, the upper bound is 1 minus 1 over n. Still. Oh, that's a very good question. Yes, so you are talking what's the case? What the LI looks like? That's a very good question. Yes, the worst case LI is I remember is that we cannot like a theoretical proof, but we observe the numerical. Usually the worst case is one LI is very large, but all the LI are very small and go to there, even close to there. So, yeah. So one LI very large, the other LI very small, go to zero. So that is the worst case. And in the worst case, you can go to 1 minus 1 over n. 1 minus 1 over n. I think that so it can be as worse as that case. Okay. So yeah. So but it's in order. I mean, we can prove in order, but we don't. I think it's wrong. I think I should have the O here. Let me double check. Okay, 1 minus.
This is surprising to have 1 minus 1 over n, because it means that if n is a little bit large,
yeah,
the price of fairness is
1.
Taking the whole cake.
Yes, that's true. That's the main insight. So here we are not sure. There may be a constant. It's capital O, but anyway, it's even 2 or 3. I don't remember this exact result. Maybe it's exact. I think so. Basically, even it's not exact, it's capital O. So that we proved that indeed. As you said, the whole cake will be gone if you are using either proportional fairness or maximum mean fairness. Yes, and actually that is surprising because we used to believe in the BFT bounds. They also show they think max mean price, the price for max mean fairness. They know it's expensive, so max mean is very restrictive. But they think PF is better. The proportional fairness should have a lower price. Which means it shouldn't cost you too much if you implement the proportional fairness. But our result said no. In the worst case, well, it all depends on the maximal achievable utility L. In the worst case, it can be also basically the whole cake is gone if you try to respect fairness, proportional fairness. Yeah. So So that I think we are still ahead of time. So basically, our bound is tight, right, for all the values. So all the value of the maximal achievable utilities, right? And basically for all the LI, our bound is tight. Our bound is the previous show you the bound. And by comparison, BFT bound is only tight for some specific values of a maximal achievable utilities. Right, so largely there's a gap here. Okay, so this is our contribution for the main theoretical contribution. So let's sum up. Let's summarize. So I think we have three contributions. First, our results complement those by the BFT. This is in the paper, right, on price of fairness. So we basically completed filled up the theoretical gap. So completed their story, right? So they showed that the price of fairness, and we show in the convex case actually. This basically in the convex case we show we derive a tighter bounds. So that close up the story. Okay, so that complement their results. And the tight bounds provides a robust insight into efficiency fairness trade-off. Those are qualitative insights because their bounds are not tight, right? Our bounds are tight. So we could speak more. For example, we could show indeed it's 1 minus 1 over n, right? But for both price proportional fairness or maximum fairness, they are actually in those extreme cases, in the worst case, they are equally expensive. And they're actually very expensive. They basically almost 1, right? So those are the insights. And we also show variance actually had a big impact on the price of fairness. If variance is small, the price of fairness will be much lower, right? But if people have different utility, then if we want to achieve fairness, it's much more expensive. And our bounds provide, I think that's a new contribution, because if you look at the read in the literature, I could name many, at least like 10 papers. Many papers are doing this. They said they find a special problem. They prove the price of fairness for this optimization problem, right? So this could be like a scheduling, right? A scheduling, and this is for I think hard allocation, any organ allocation, actually, right? Hard allocation. Ma is for, I think, is for inventory. Right. So, and there are some other paper about the facility location. So for all those special program instance, you could implement a bound, and by exploiting the program structure, you could derive maybe the POF bound, but with a lower value, because you have a special problem. Your price of fairness could be much lower, right? But what our bound can be, I think it can provide first upper bound. Right? No matter what you are doing, your bound, as long as the utility set is convex, which is usually could hold, our bound provides the upper bounds. So if your bound is larger than our bound, I think something is wrong. Right? Our bounds must be an upper bound, because we are talking for general problem instances. And also we get a benchmark. This is the benchmark. Because if you say for facility location, right, price of fairness I proved like 70%. Is 70% good or not? Right? Well, you could use our bound as a benchmark, because that's for the general problem. For general problem, it's already 70%. You prove 70%. That's not much improvement, right? If our bound is like 80%, you get 70%. Then you make some improvement, right? So basically, I think our bounds can provide a unified like upper bound and benchmark for all those growing body of research which are doing calculating of a POF for special problem instance. But I'm not saying, I think they are very interesting work. I don't say they, right? They are very interesting work that by exploiting the special problem structure, right? For special problem instance, you try to calculate the POF. I think that's that's still very interesting and technically challenging work. Okay, so that concludes my talk. Thank you very much.
Thank you.